Cindy Kelly, Atomic Heritage Foundation. It is Wednesday, April 25th, 2018. Adam, would you please say and spell your name?
Adam Justin Rondinone, A-D-A-M, J-U-S-T-I-N, Rondinone, R-O-N-D-I-N-O-N-E, and that's Italian.
Terrific. So Adam, you're here at the Oak Ridge National Laboratory, and you must be a scientist. Why don't you tell us something about your childhood and where you were born and how you came to be a scientist?
Mm-hmm. So I was actually born in a somewhat rural town in New Hampshire, and I've always loved science ever since I was a kid. In fact, I inherited my love of science from my parents. I think in a different life, my dad, who was a watchmaker, probably would have been a scientist. He just didn't have that opportunity. But he was always interested in things that were mechanical and electronic, and he taught me about those things ever since I was really just a little child, maybe 5, 6 years old. And then at some point when I was a kid, my parents bought me a set of encyclopedia called the Young Children's Science Encyclopedia. And that was a set of books just filled with experiments that could be done at home. And I did these experiments. I probably did most of them, the ones I can get my hands on, the materials. And that really just fed my love of science. And so when I went off to college, it was just that was what I was going to do. And I did my graduate school at Georgia Tech. And when I was a graduate student at Georgia Tech, I would actually come to Oak Ridge to do experiments as part of my graduate work. And so Oak Ridge has these facilities that we call user facilities. These are large science investments that the federal government makes and makes these capabilities and these facilities open to anybody that wants to come here and use them to do science, as long as they're going to publish it in the open literature. And so I would come here periodically as a graduate student, do my experiments, go back home, wrote up my thesis, and then when it came time to look for a job, Oak Ridge wanted me to come here, so I came here, and I've never really left.
That's fabulous. Now you're working, tell us what you're working on now.
So my science is about nanotechnology. And nanotechnology is a field of material science where we take common materials that we know about in everyday life, plastics and metals and ceramics and things, and we make them very, very small so that they start to take on the properties of molecules. And so this is kind of the intersection of normal chemistry and material science or metallurgy. And what's interesting is when you take a normal material and you scale it down to something very, very small, cluster of a few atoms, for example, it takes on new properties. So in that sense, it becomes a new material. So if we think about gold's a classic example of this. Gold as a metal is so unreactive, we find it in nature as a metal. We make jewelry out of it. We coat our contacts with it for your high definition audio headphones so that they won't corrode. Very, very unreactive. But as it turns out, if you take gold and you make it into a nanoparticle, that is a clump of just a few atoms, it becomes a potent catalyst for chemical reactions. And this is just a great example of how we can take common materials that we know everything about pretty much at this point, change the scale to make them very small, and really it's a whole new material. So we study nanotechnology, and then my personal research is about how to take the principles of nanotechnology and solve energy problems. And so we study a field of chemistry called electrochemistry. Electrochemistry is familiar to people in the form of batteries and fuel cells. And so we basically are developing new types of energy storage and conversion systems based on nanotechnology. We're best known right now for a reaction that takes carbon dioxide, which is a pollutant, and converts it into ethanol, which is a commodity, and it does so at very high yield and high efficiency. And that process is actually being commercialized now.
That's very exciting. Very exciting. Tell us more.
We recently discovered a reaction where we can take nitrogen gas, which is in our atmosphere, and mix it with water and renewable electricity and convert it into ammonia. Now, this is interesting because ammonia synthesis is used for fertilizer. Fertilizer is used for modern farming. And most people don't know that ammonia consumes, or the synthesis of ammonia consumes about 3% of the world's energy. That's a huge number. And also, it releases about 3% of the world's carbon dioxide emissions into the atmosphere. And so we think this is a great target because if we can eliminate CO2 emissions from ammonia synthesis, then we can cut 3% out of our emissions portfolio, and that's a big deal. Also, ammonia right now is synthesized using the Haber-Bosch process, which is a wonderful process, been around for a very long time, but it requires very high temperatures and high pressures, which makes it expensive. And so easy for us to do in the United States, not so easy for other countries that are less developed than the United States to make ammonia. And so they tend to be ammonia poor, which means they're fertilizer poor, which means they don't grow enough food. And so if we can develop a way to synthesize ammonia using electricity, in particular renewable electricity, we can do away with the natural gas and the CO2 emissions, we can do away with the high temperatures and pressures, and then we can make ammonia at room temperature, low pressure, which means we can do it in a distributed fashion. So individual farms can make their own ammonia, which means they can make their own fertilizer, and that really just helps everybody.
Did you come up with this idea, or did your team come up with this idea?
So I'm going to take credit for these ideas, actually. Maybe 7 or 8 years ago, I was discussing with my colleagues. We were sitting in a symposium, and we were watching the presenter talk about his science. And this typically happens in science, right? We get together, we have these conferences, and we do that because it generates new ideas. And so I turned to him and I said, "This is an interesting material this person's working on. Can you make it for me?" And it was a type of textured graphene. And my colleague said, "No, I can't make that particular type of textured graphene." Graphene, by the way, is a nanomaterial version or a nanotechnology version of graphite. It's a single atom thick layer of carbon. It has very interesting properties. But without getting too far into that, I asked him if he could make this particular type of graphene, and he said, "No, I don't think I can make that, but I can make something that's pretty close. Let me go into the lab and figure it out." And this gentleman's name is Dale. He went into the lab and he tried to make this textured graphene for me. And he made something different, but it turned out to be very interesting. It turned out to be a very good electrochemical catalyst, nanotechnology-based electrochemical catalyst, that happens to do very well at complex electrochemical reactions involving things like nitrogen and CO2. And this carbon is actually the basis of our catalyst technologies that we've developed for converting CO2 into ethanol, converting nitrogen into ammonia, and it actually does some other tricks too that we haven't published yet. And this is typical in science. Everybody in science is kind of unique. We're all like artists. And so one artist might be able to paint a certain type of painting, another artist can paint a different type of painting. And this creativity and this vibrancy is really what allows us to generate new ideas on a continuous basis and pursue those ideas. So science really is, it is about facts, it is about careful measurements, it also is about creativity.
Very much, sounds like. What about, you described the fact that you go to conferences and they're very stimulating. Tell us about the sort of collaboration that happens in science today.
So science is a worldwide collaboration, which means that there are thousands of scientists all over the world who are constantly working with and competing against each other in a somewhat friendly sense. So we all want to be first. So we want to publish a paper that says that, you know, we made this discovery and we're going to get cited and known for that. And occasionally we get lucky and we are first at something. Most of the time we're second, third, or 10th. And so, but we work together in a friendly way across borders. And governments recognize this. They fund us to do this, which is why we travel around the world. Not so much around the world these days, but mostly in the United States. But every now and then we go to Europe. So but the scientific enterprise is really meant to be beneficial for everybody. We tend to focus on basic science, which means that it's prior to the application. And so a way of thinking about this is an application for say glass is your cell phone, right? The basic science behind glass is how do we take sand and purify it, right, and make it into glass. And so once we figure out how to take sand and purify it and make it into glass, and we share that knowledge, then that's good for everybody. And so governments around the world invest in science with the recognition that the basic knowledge that we develop goes on to help everybody. And then at some point that basic knowledge gets picked up and it moves into an application, and then that might be something that becomes proprietary or secret, and we don't want to share that because it gives us an advantage. But basic science, because it's meant to help everybody, allows us to be collaborative. And it allows us to work across borders. And we work, and we're funded by, in my case, we're funded by the federal government, but companies fund scientists, foundations fund scientists, other governments fund their scientists, and we all get together and we share our results publicly. Sometimes we'll patent those results before we share them, but we'll share them, and usually we'll do this in a publication. And we also get together in conferences where we meet, we present, we talk, we yell at each other and ask questions, and it's a great opportunity to sort of cross-fertilize new ideas.
Federal budget's under great scrutiny these days. What's the economic impact of publicly funded science?
So Congress funds scientific research in this country with the intent that it's going to help everybody. And so the knowledge and the information that we discover, it gets reported. And it gets reported in journals. In some cases, we put it out in the popular press. Occasionally, we'll make a YouTube video and put that on the internet. And the idea behind it is that if the basic knowledge is discovered, then a company or a government or anybody can take that basic knowledge and use it to make some type of an application. So solve a problem, essentially. And solving problems makes people's lives better. Oftentimes, solving a problem gives us new economic opportunities, so we might be able to found a new company and put people to work. And so in my case, where we're looking at nanotechnology approaches to solving energy problems, the expectation is that if we're wildly successful 10 years down the road, we might be able to say, instead of drawing energy from fossil fuels, where we have to bring that up out of the ground, we can draw our energy from renewable sources, such as windmills and solar panels. Well, that's an opportunity for renewable energy. It's also an opportunity to minimize environmental impact. And so governments fund basic science with the intent of making people's lives better and making the economy stronger and more competitive.